Hi everyone and welcome to another video. Today we're going to be learning how to represent a complex number on a complex plane, or what some books or some teachers may call an Argand diagram. It's going to be an interesting topic. There'll be a lot of things to learn in it. Just get ready, get your cup of coffee, get your notebook, sit down and let's learn something new. Alright, now we look at the Argand diagram. Now, in some places of education, in some countries, or depending on who the teacher is, the Argand diagram may also be referred to as the complex plane. Alright, but basically, complex numbers can be represented graphically on a graph of real and imaginary axes called an Argand diagram or a complex plane. So you can represent every complex number we've done so far on a diagram that has different axes, a real and imaginary one. Alright, so let's look at some definitions. Now this one you may be familiar with already because you've already done it before, because modulus is the magnitude of a complex number. So you've already done this before, but we're going to do more of that again in this section. Now we're going to be introduced to a new term, which is argument. So what is an argument? An argument is the angle measured from the positive real axis up to the given complex number. The argument of a complex number z is denoted by argz, and it ranges from negative 180 to 180 degrees. So pay attention to that. So the value can never be bigger than 180 degrees, but also it can never go below negative 180 degrees. And then we are saying if measured in degrees, it is that. And then if it is measured in radians, it's negative pi to positive pi. Of course, we know pi in radians means 180. And then we can actually see that. So this is the rule for arguments. So now in most of the numbers that we shall be doing, I'll also be representing my arguments as theta. So I'm going to be using theta preferably by choice to also represent arg, as we shall look at it. So on an Argand diagram, a complex number is represented by a line with an arrow on the head to show the direction. So let's look at the different states of Argand diagrams. So saying positive angles are measured in an anti-clockwise direction from the positive real axis. Thus, complex numbers which lie in the first and second quadrants have positive arguments as shown below. So let's look at the different complex numbers in the first two quadrants. So let's look at the first quadrant. So the first quadrant is one where we have these are the real and imaginary axis. So the real axis is on the x-axis. If you've worked on lines diagrams before where there is an x and y, you can actually see that the real is on the horizontal axis and the imaginary is on the vertical axis. And as usual, this is actually 0. So 0 denotes the value right here at the middle. Alright, so now we're going to place the first illustration. So now here is an example of a complex number where we have a positive a value and a positive b value. Now that means they're going to be in the first quadrant. That is because just like in any other number line diagram, this first quadrant here represents the region where all values of the horizontal and in the vertical are positive. So this is going to be the first one. So that means our line is going to be, our complex number is going to be in this region. So that's why I'm saying z is equal to a plus bi is there. So now we have the coordinates on the real axis. So the real value is a and the imaginary value is b. So that's why we have b on the imaginary and a on the real axis, because you can see here that bi is the imaginary side and a is the real side. And then lastly, we're going to put our argument. So our argument is basically the angle that this line that we've written here, the line representing the complex number, makes with the angle it makes with the horizontal axis, which is the real axis. So that's what argument z represents. So my argument z is also going to be represented by theta, as I'll show you in different examples. Alright, so therefore argument of z, which is also equal to theta, is the same as tan inverse of b over a. And why is that? It is because you remember from trigonometry that from the formula SOHCAHTOA that t is opposite over adjacent. And as you can see that the opposite of this angle is this side, and then the opposite can also be represented as this b. So this distance here is the exact same distance here, so that's the distance b, and then the adjacent of this angle is this a, so that's why we actually have it as being equal to tan inverse of b over a, so that's why we find it that way. And then we can actually see that when we are trying to find its modulus as usual is the same as root of a squared plus b squared. So we're going to square the real and square the imaginary, and then the answer we get from adding them and the root we get is actually going to be the modulus of that. So that's for the first quadrant. Now what if we go into the second quadrant? So in the second quadrant, definitely this is the section where we have the negatives on the horizontal axis and still positives on the vertical axis. So this is how it looks. So now this is an illustration of where we actually have a negative a and a positive b. That's why we're actually in this region here. As you can see that a here is negative and b is positive. So this is why we are in this region. And now there is going to be some difference here. Remember that argument is what we measure starting from the horizontal axis towards the anti-clockwise direction. That is in this case because when we're dealing with the first and second quadrants, we do anti-clockwise rotation, so the answers are going to be positive. So for this case, we cannot find this angle directly. We cannot find argument z directly. So that means we're going to first find what alpha is. We're going to find the value of alpha is, and then we're going to subtract that from 180 and we'll get the argument of z. As you can see, therefore the argument of z, which is theta, is going to be equal to 180 minus alpha. So we're going to find alpha first, and then the answer we get, we subtract it from 180 and we'll get the value of the argument of z. Alright, so therefore we have that, and then now we can actually see that we'll actually have this. So now the value of alpha is tan inverse of b over negative a. But now for this case, we're only going to use this negative here to just simply represent the position of the real on the real axis, but we don't want that negative sign to affect our final answer, so that's why we'll put it in this sign, in this modulus sign, because we want to make sure that the answer we get from here is positive. So ignore the negative while doing calculations, because the negative just simply represents the direction or the position on the real axis. So that's why we end up having 180 minus whatever we have there. So we need a positive answer at the end. But as usual, the modulus of z shall be equal to this. So definitely the answer here shall be the same as that, because the square of a negative is still a positive, and then we'll end up having that. So that's it when we are dealing with the second quadrant, where we have a negative of an a and a positive of a b. Alright, so now the reason we cannot go past this is because we've made a rule that we cannot go past 180. So the biggest value we can get is 180. So now the only other options is when we're dealing with the third and fourth quadrant is now we'll be doing clockwise rotations for the other side. Alright, so negative angles are measured in the clockwise direction from the positive real axis. Thus, complex numbers which lie in the third and fourth quadrants have negative arguments as shown below. Alright, so now when we're dealing with the third quadrant, so the third quadrant is now definitely a region where we have a negative on the vertical axis and a negative on the real axis. So a negative on the horizontal and negative on the vertical. So of course the vertical means the imaginary, and then a horizontal represents the real. So let's put our points there. So this is our complex number. So it's negative a minus bi. So that's why it's in the third quadrant of negative, negative. So let's place it there. As you can see, the same thing happens almost like what happened with the second quadrant. You can actually see we can also not get the value of argument z directly, but obviously in this case we are doing negative revolutions. That means the answers we get from this should be negative because we're doing clockwise rotations. So what happens in this case, we're also going to first find the value of alpha, and we shall use that to get argument of z. So in this case we can actually see that since we're doing clockwise rotations, whatever answer we have, there shall be a negative, shall be negated from the outside. So we have 180 minus alpha to get argument of z with a negative outside because we're doing clockwise rotations. And then when we put this negative inside the brackets, we can actually see it affects this, and we'll end up with alpha minus 180. So this is exactly the same as that. So we can actually see that when we find the value of alpha, alpha is the same as tan inverse of negative b over negative a, of which the negative simply represent the position on the Argand diagram, but we don't want that to affect our answer. So that's why we do this, so that we end up having a positive answer. All right, doing that minus 180. So when we do that, we will get the value of theta, or the value of argument of z. Now we can see that the modulus of z is the same as that. All right, so when you deal with the fourth quadrant, so fourth quadrant is now where we have a positive on the real axis and a negative on the imaginary axis. So let's look at how this is. So we now have a minus bi, so that's a negative on the imaginary and a positive on the real. So when we place that, we can actually see we can get the argument of z now directly, so we don't need to deal with alpha now. So in the fourth quadrant, we can actually handle this directly. So how do we do that? We can actually see that obviously the answer is supposed to be a negative, so that's why we negate whatever we have this. That's why we have a negative here, because the answer is going to be negative. Negative of tan inverse of negative b over a. So pay attention to this, because the answer from here must be positive, and then we'll negate it. So while doing tan inverse, we do tan inverse of something positive, and then we negate that. And then we can actually see that modulus is found from that formula. Alright, so let's look at some examples. So this will help us have a better understanding of what we've just discussed. So being asked to represent each of the following complex numbers on an Argand diagram, and hence find their modulus and principal argument. So A is that, B is that, C is that, D is that, and E is that, and then F is that. I believe after we've gone through each one of these examples, you'll have a better understanding on how to represent them on an Argand diagram. So let's look at part A. So part A is 1 plus I, so definitely this has a real, a positive real, and a positive imaginary. So that means we're dealing with the first quadrant. So we're going to place our complex number in that first quadrant. So here it is in the first quadrant. As you can see, we have a 1 on the imaginary, and we have a 1 on the real. So that's how we actually have 1, 1. So next we're going to put the argument on the diagram. So this is going to be where the argument is, or the value of theta. And then we can actually see that, let's first find the modulus. Modulus is going to be 1 squared plus 1 squared, which is equal to root of 2. Then that to be root of 2 units. And then we can actually see that argument of z is definitely tan inverse of 1 over 1, and of which the answer is 45 degrees. As easy as that. So let's look at part B. So part B, we have negative 1 minus root of 3i. So this is a negative on the real and a negative on the imaginary. So that means this is actually the third quadrant. So in the third quadrant is where we have negative, negative. So we place it right there, and as you can see, we now have an alpha to deal with before getting the value of the argument of z. And as you can see, obviously, since we're doing clockwise rotations, in this case, the answer is going to be a negative angle. So how do we do this? Let's first find the modulus. You can actually see that the modulus is going to be 1 squared plus that squared, and then we'll end up with 2 units, because the answer from here is 1, then the answer from here is 3. So 1 plus 3 is 4, and root of 4 is 2 units. Alright, so now we can see that to find the value of theta, or argument of z, we can actually see that now we're going to first have to find the value of 180 minus this, of which we know we have to negate the answer because we're doing clockwise rotations. So substituting into this formula, alpha minus 180, we can actually see that alpha is going to be tan inverse of, remember now we're dealing with, so negative 1 and negative root of 3 simply represents the positions on the Argand diagram, but we don't want those negatives to affect our answer. So we're going to treat the answers here as positives. So we end up dealing with tan inverse of 1 over root of 3, of which the answer shall be equal to 30. So 30 minus 180, and the answer is going to be negative of 120 degrees. And that is going to be our answer for the argument of z. Let's look at part C. So part C is a little bit unique. Part C, the answer, we have negative 5. So this is an example where we have no imaginary side. So that means the imaginary side is equal to 0. So how do we represent this on our Argand diagram? Now this is different. So how do we place that? As you can see, we're going to place the -5. As you can see, the -5 means a negative on the real axis. So we plot it right there. And then in this case, the imaginary part is equal to 0. So this is where it's going to be. So basically, our complex number line, the line is just going to be basically this. So here is our line right here. And then as you can see, since we are finding argument of z, the argument of z in this case can be found directly. So we simply move from here to there. So the argument of z here can be found directly. So as usual, the modulus of z is going to be equal to 5 units from this case. But now we can actually see that the argument of z can be directly seen and directly gotten, and it's going to be equal to 180 degrees. Right, let's move on to part D. Part D is -√3 plus I. As you can see, this is going to be an example where we're going to be in the second quadrant because we're dealing with a negative real and a positive imaginary. And then let's place that right there. So we have that right there. Now we're also going to have to first find the value of alpha. So we're dealing with anti-clockwise rotation, so the answer is definitely going to be positive. So let's first deal with this. So the modulus is going to be equal to 2 units. And then to find the argument of z, we can actually see that we'll have to do 180 minus the value of alpha. So what is the value of alpha? The value of alpha is tan inverse of 1 over -√3. But as you can see, we don't want a negative here. So we're going to treat this as a positive. That's why we put these bars here. So we're going to be treating it as 1 over √3 because the negative simply represents the position on the real axis. And as you can see, tan inverse of 1 over √3 is going to be equal to 30. So 180 minus 30 is equal to 150 degrees. Alright, let's look at another example. So now this is an example where we have a positive real and a negative imaginary. So this is an example where we're going to be in the fourth quadrant. So let's place that in our fourth quadrant, as you can see there. So this is what we're going to have. So this can be found directly. We don't need to find any value of alpha. So the modulus is direct and it's going to be equal to 2 units. Then we can actually see that the argument of z is obviously going to be a negative because we're doing clockwise rotations in this case. And then we're going to negate the answer that we get because we are moving in the clockwise direction. And as you can see, we have tan inverse of this. So we're going to treat this as 1 over √3, of which tan inverse of 1 over √3 is going to be equal to 30 degrees. But because there is a negative here, it's going to be equal to negative of 30. Alright, let's look at the last number. So this is an example where we have 0 on the real and we have a positive imaginary. So we're going to place the 3i there. So we have the 3i on our diagram. So we have the 3 on the imaginary and then we have a 0 on the real. So this is how it's going to actually be. As you can see, to move from the positive horizontal, we're going to move at an angle of 90 degrees. So this can be seen directly. You can already see that modulus is obviously going to be equal to 3 units, but you can actually see that the argument of z is clearly equal to 90 degrees. So that can be seen. There's no need of any complex calculations. Alright, so let's look at an example from UNEB chapter UNEB 2011 question number 10b. So given that z is equal to -1 plus √3i and z2 is equal to -1 minus √3i. So we're being asked to express z1 over z2 in the form a plus bi √bi, where a and b are real numbers. The number 2 represents z1 over z2 on an Argand diagram. And then part 3, we're being asked to find the modulus of z1 over z2. So let's solve this. As you can see, the first thing we're required to do is to simply simplify. So when we get z1 over z2, now we're dealing with 2 complex numbers dividing. So it's an example of division of complex number. And as you can remember, we multiply both the top and bottom by the conjugate of the bottom. So that's why we end up having that. And then when we open brackets and do some multiplication, we end up having this and that. As you can see at the bottom, this and this will cancel. And then at the top, we end up having -2i, 3 root 3 at the top as that. And as you can see that 3i squared, we know that I squared is equal to negative 1, so we have a negative 3. 1 minus 3 is negative 2, so that's why we have that there. Then also at the bottom, we know that I squared is again negative 1. Negative 1 times negative 3 is positive 3, so 3 plus 1 is 4. And as you can see, you can divide the 4 on both sides, and then we end up having that. So negative a half minus I root 3 over 2. Alright, so next we're asked to represent this on an Argand diagram. So this is what we have. So as you can see, we have a negative a half and a negative root 3i. So that means we're dealing with the third quadrant where we have a negative real and a negative imaginary. So that's where we're going to place it. So we're going to end up with something like that. So that's how it will look on our Argand diagram. Alright, so part 3, we're being asked to find the modulus of that. So as you can see, we know that the modulus is simply equal to that in that formula. So we know that a negative a half squared is 1 over 4, and negative root 3 over 2 squared is 3 over 4. As you can see now, when we add those two fractions, we end up with 4 over 4, of which now that becomes a root 1, and root 1 is equal to 1. So therefore the modulus of z1 over z2 is equal to 1. Alright, let's look at an example from UNEB November 1998, and this was question 9a. So being asked, given that z1 is equal to negative 1 plus I, z2 is 2 plus I, and z3 is 1 plus 5i, represent z2 times z3, comma, z2 minus z1, and 1 over z1 on the Argand diagram, and also show the representation of z2 times z3 over z2 minus z1 plus 1 over z1. Alright, so we're going to represent all these on an Argand diagram. So how do we do this? So first step is we better simplify all these three formats that they've given us here. So how do we do that? So let's first deal with the z2 times z3. And then for that we have that. So we have these two complex numbers multiplying themselves. So basically this is basically a multiplication of complex numbers. So when we open the brackets, we know we end up having that because we have 2 times 1 is 2, 2 times 5i is 10i, then I times 1 is I, and then I times 5i is 5i squared. Now we know that 10i plus I is 11i, and 5i squared, we know that I squared is negative 1, so we have a negative 5. So we end up having 2 minus 5 is negative 3. So we end up having negative 3 plus 11i for the first part. So when we deal with z2 minus z1, we know that these are the different complex numbers that we actually have. So let's open those brackets. When we open those brackets, we can see that the negative there becomes a positive, and then we have a negative I. So when we subtract, we can see that i's cancel, then 2 plus 1 is 3. So that's what we end up having. So let's deal with 1 over z1. We know that this is simply an inverse of z1. So we have 1 over negative 1 plus I. Now in such an example, it's more like a division of complex numbers, and we know that in such cases we multiply both top and bottom by the conjugate of the bottom, and that's why we end up with that. The conjugate of the bottom is negative 1 minus I. Alright, so when we open the brackets, we end up having that. So at the bottom, I minus I is 0, so we are left with 1 minus I squared, of which we know that I squared is equal to negative 1. So negative 1 times that negative is a positive 1. So positive 1 plus positive 1 is 2. So we have a 2 at the bottom. And then when we split the bottom value between the two numerators, we end up having negative a half minus I over 2. So now we've dealt with these three, and then right now we'll be also asked to represent this on an Argand diagram. Now the good thing with this is just basically repetition. So we have the value that we got from z2 times z3 over z2 minus z1 plus 1 over z1. So we're just going to basically represent these others that we've actually found there. So just going to substitute them in. So this is what we have. So we're going to substitute in the values. So now where there is z2 times z3, we substitute in this. Where there is z2 minus z1, we substitute in this 3. And then where we have 1, when we have 1 over z1, we substitute in this value, which can be simply, with which the LCM is 2, so it can be basically represented as that. So now as you can see the LCM from here, the LCM is going to be equal to 6, and then we end up with that. And then we can actually see that 22i minus 3i is going to be equal to 19i, and then negative 6 minus 3 is negative 9. So you end up having negative 9 plus 19i over 6, of which that in decimal form is negative 1.5. So when we split the 6 between the two, we can actually say negative 9 over 6 is negative 1.5, and then 19 over 6 is 3.17. So we end up having that as our representation. So this is the simplified format. So this is everything we have here in the form of a plus bi. So that's what we have. Right, so when we represent that on an Argand diagram, so this is going to be an Argand diagram. So we're going to represent each and every single one that we've been shown, because we're supposed to represent all on the second on the Argand diagram. So let's deal with one at a time. So the first one we're going to deal with is Z2 times Z3, and remember that for that we found in the most simplified form it was equal to negative 3 plus 11i. So there was an 11 on the imaginary, and a positive 11 on the imaginary, and a negative 3 on the real. So that's why we end up with something like that. And then now when we represent the Z2 minus Zi, we can actually see that we did not have an imaginary part to it. There was only a positive real part. So that's why we have it drawn that way. There's only a positive real represented on that. So that's why we have it horizontally on the real axis, because there is only a real, so it's exactly on the real axis like that. So let's represent the next one. So now when we remember that 1 over Z1 was equal to negative a half plus minus a half I. As you can see, this is how basically we represent it. So it's going to be a negative a half. Yeah, it's going to be a negative a half and a negative a half. So that's how we represent that. And then lastly we're going to present the last one, and then the last one was the final one. So remember we just got it as negative 1.5 plus 3.17i. So now representing, putting 3.17 on the imaginary and the negative 1.5 on the real. So is what we end up having for this equation. So that's how we represent this on an Argand diagram. As simple as that. Alright, so let's look at modulus argument form, and let's look at what this actually represents. So it's another important part that we need to have an understanding of. So the modulus argument form, or polar form, so mark that it's also referred to as polar form of a complex number z, consists of modulus r. So right now we're going to represent the modulus with the letter small r, which is the distance, the origin, and the argument theta. So as usual, we're going to also represent our argument with theta, which is the angle the line makes with the positive x-axis. So imagine we have an Argand diagram here. You can actually see that the r is going to represent the distance of that from the origin. And then right now we have the x representing the values on the real, and then the y representing the values on the imaginary. So now theta is going to represent our argument, as you can see right there. So consider a complex number z is equal to x plus yi, and that's what you're seeing there, making an angle theta with a positive axis. You can see that the argument of z is equal to 0, and then from the diagram we know that cos theta is equal to x over r. Remember that cos means adjacent over hypotenuse. Of course the hypotenuse is equal to r and the adjacent is equal to x. So x is the adjacent to the angle theta. So we end up having cos theta being equal to x over r. Then sin theta represents opposite over hypotenuse. So the opposite of the angle theta is y. Then the hypotenuse is r. So that's why we have y over r. Then as you can see, when you make x a subject in the first one, we have x is equal to r cos theta. And then we have y being equal to r sin theta in the second one. But remember that z was equal to x plus yi. So that's the complex number that we're dealing with. So now when we substitute in replacing the values of x and y, we end up having that. And then we can actually pull out the r. We can factorize it out. Then we remain with r cos theta plus I sin theta. and this is actually the modulus argument form. So this is what you have to memorize and remember. But we also know that r, which is now representing the modulus, is now also going to be equal to root of x squared plus y squared. So that represents the modulus of that, of the complex number that we're dealing with. Alright, let's look at a few examples, and this will help us have a better understanding of this. So we're going to deal with these 3 examples that I've just given you here. So let's look at part A. Part A, we're dealing with 3 plus 4i. Definitely, this is an example where we have a positive imaginary and a positive real. So we're dealing with the first quadrant of our Argand diagram. So let's place that in our first quadrant. So we end up having it like that. So we have the 3 on the real and the 4 on the imaginary. And then right now we're going to represent the argument with a theta. But right now the r value is still unknown. We don't know the distance from here to here, and we're going to find that out in our calculations. As you can see, to find the argument of z, remember that we get z by tan inverse of 4 over 3, and you can see that argument of z, which is theta, is going to be equal to 53.1 degrees. So the argument, which is theta, is going to be equal to 53.1. So now we can find r from finding the modulus. So modulus r is going to be equal to 3 squared plus 4 squared, and the root of that is going to be equal to root of 25. And then we know that root of 25 is equal to 5 units. So now we can place the 5 right where we have the r, so that is now known. And then right now, from the modulus argument form, which is what we have here, we can see that z is going to be equal to 5 into cos 53.1 degrees plus I sine 53.1 degrees with the 5 outside. And that's what we have as the modulus argument form. Alright, let's go to the second one. So we have a negative 5 minus 12i. So definitely this is a negative real and a negative imaginary. So basically we're dealing with the third quadrant. Alright, so let's place it all in the third quadrant. And as you can see, this is what we end up having. So we cannot find theta directly. We have to first find the value of alpha before we find theta. So we know that to find it, we know that we have to have a negative of 180 minus alpha, of which that is the same as alpha minus 180. And then we know that alpha is tan inverse of negative 12 over negative 5. But now we need a positive answer from here, so we're going to place it in between these bars so that we only get a positive. So tan inverse of 12 over 5 is going to be equal to 67.4 degrees. So we have a 67.4 minus 180, of which now theta is going to be equal to negative 112.6 degrees. Alright, now to find the modulus argument form, we know that now we have to find the root of negative 5 squared plus negative 12 squared, which is equal to root of 169, which is equal to 13. And then in the modulus argument form, z is equal to r cos theta plus I sin theta. We can actually see that we can substitute in the values. Then you end up having z is equal to 13 brackets cos of negative 112.6 degrees plus I sin negative 112.6 degrees. Now you can leave it this way, or you can also choose to simplify this. Now with the knowledge of trigonometry, we know that when you have a negative in the cos, you can actually just ignore the negative sign. But also when you have a negative where there is sign, that this negative affects the sign in front of the sign itself. So what you can see is this can be simplified to look like that. So this negative affects this positive, and then we have a negative there, and then we simply ignore this negative and we are left with that. So this is a more simplified version of expressing it in modulus argument form. Alright, let's look at the last one. So the last one is negative 5i. So right now the real part does not exist, so we are dealing with a purely imaginary number. As you can see, we're only going to put that in the area where we have imaginary, a negative imaginary, and that is somewhere there. So this is what is going to look like on our diagram. And as you can see, we're doing clockwise revolutions, and this is going to be a revolution of 90 degrees. So that can be seen directly. So it's a revolution of actually negative 90 because we are moving in the clockwise direction. So theta ends up being equal to negative 90 degrees. And then r can be found from that, and then you know that r is going to be equal to 25 inside the root, which is equal to 5 units. And then we can actually see that z is going to be equal to r cos theta plus I sin theta. Alright, now you can see substituting into the modulus argument form we have that. And then when we choose to simplify that, as you can see in a more simplified form, we can choose to ignore the negative in front of the cos, and then the negative in the sign, we can bring it here and it will affect that, and then we'll end up having that. So this is the more simplified way of expressing it, but both ways will work. Alright, so let's delve deeper into the concept of arguments. So we're going to look at some properties of arguments. Now these properties are going to help us in solving some different numbers. So these are going to be very important. So given two complex numbers z1 and z2 with moduli, so imagine the modulus of z1 is that and the modulus of z2 is that, and arguments argz1 and argz2 respectively, then we can see that when it comes to multiplication, we remember this from the very beginning, and we actually have two different complex numbers multiplying themselves. If we want the modulus of their product, that it can be the same as this. It can be the same as the modulus of each individual one, as you can see there. And then also the same thing applies with arguments. So when you have the product of different arguments, so when you have the argument of z1 times z2, it's the same as argument of z1 plus argument of z2. So that's going to be for multiplication. So those are going to be important to remember. So for division, you can actually see that also when it comes to modulus, you know that if we have to find the modulus of z1 over z2, it's the same as the modulus of z1 divided by the modulus of z2. And then when it comes to arguments, you can say the argument of z1 over z2 is equal to argument of z1 minus argument of z2. So that's also going to be important to remember. Now also when it comes to powers, we can see that when you have a power inside a modulus, that power can be taken outside the modulus and can also be expressed that way. And then also when it comes to arguments, you can actually say that when you have the argument of z1 power n, you can see that it's the same as n times argument of z1. So that's going to be important to remember. So memorize those and note them down. Alright, so let's look at an example from UNEB 2019, and this was question number 1. So we're being asked to show that the modulus of 1 minus I power 6 over 1 plus I is equal to 4 root 2. So let's simplify this first. As you can see that we're being asked to show that the modulus, so the modulus of this can be expressed this way. But we know from what I've just shown you that this can be the same as that. So it's the same as the modulus of this individually divided by the modulus of this individually. So it can actually look like that. And also you can say that we can take the power outside the modulus, and that's why we have the 6 outside that modulus. And as you can see, we can see that now to find individual modulus, the modulus of the top is going to be equal to root of 1 squared plus negative 1 squared. And then we're going to keep the 6 outside. Then at the bottom, the modulus is 1 squared plus 1 squared and the root of that. So at the top, we're going to get the answer as root of 2, and at the bottom, the answer is also going to be equal to root of 2. And then the power 6 is still outside. Now you can see that we have the same number both at the top and at the bottom. So you can see that this can be expressed as root of 2 in power 6 minus 1. So we end up with root of 2 power 5. Now we know that root of 2 power 5 is the same as root of 2 times root of 2 5 times. Now root of 2 times root of 2 is 2. So we have that times the next 2, which is going to be 4. And then 4 times root 2 is going to be equal to 4 root 2. So this is going to be our answer. Alright, so let's look at a question from UNEB 1996, question 10a. So we're being asked that given that that z is equal to root 3 plus I, find the modulus and argument of 1 z squared, 2 1 over z, and then show in an Argand diagram the points representing the complex numbers z, z squared, and 1 over z. So now the first thing we're going to do is we're going to first so we know that z is equal to root 3 plus I. So we're going to first find what what the modulus of z is, because that's going to be important. We're being asked to find the modulus and argument of each individual one. So before we even find this, let's first find the modulus and argument of this z here. So its modulus is going to be equal to root of 3 squared plus 1 squared. So that's the same as 3 plus 1, which is going to be equal to root of 4, and root of 4 is equal to 2. And then when we find the argument of that, we know that this we're dealing with a number in the first quadrant of the Argand diagram. So definitely for here the formula is going to be tan inverse of 1 over root 3, which is equal to 30 degrees. Now that's important because here this is basically the first quadrant. So by now I hope you've memorized and can look at a complex number and know which quadrant it lies in, so that we quicken the process of finding argument. So the argument is going to be equal to 30 degrees. So now let's deal with the first one. So for the first one, we know that z squared is the same as, alright, let's first find its argument. So we know that argument of z, we know that the formula argument of z n, so when you have z with the power, we know how to bring the power outside and multiply it by the argument of that number. So this was our formula. So this is basically for a reminder. So now when we find the argument of z squared, we know that that is going to be equal to 2 times argument of z. But now the argument of z is known. We know that the argument of z is equal to 30 degrees. So that means we have 2 times 30 degrees, which is equal to 60 degrees. So now when we go to finding the modulus of that, we know that modulus of z squared, we know that we can take the power outside the modulus, but even without doing that, we know that this z squared is the same as z times z, of which that is the same as modulus of z times modulus of z, of which we know that modulus of z is equal to 2. So that's the same as 2 times 2, which is equal to 4. Alright, so that's it for the first part. So let's go to the second one. So the second one, we're dealing with 1 over z. Not 1 over z is the same as z power negative 1. So it can be expressed that way. And now we know that from the modulus, from the argument, from powers of arguments, we know that this was the formula we were given. So now we have an argument of z power negative 1, which is equal to negative 1 times argument of z. So argument of z is known and it's equal to 30. So we have negative 1 times 30, which is equal to negative 30 degrees. So we found the argument. So let's find its modulus. So now we know this is the same as 1 over z, which can be separated as modulus of 1 over modulus of z. And then we know that modulus of 1 is equal to 1. And then we found from our calculations that the modulus of z is equal to 2. So that's what we end up with. We end up with a half. Then when we go to part 3, we're being asked to represent that on an Argand diagram, to represent each one on an Argand diagram. As you can see, let's first plot the first one on there. So these are our real and imaginary axes. So as you can see, let's plot z. We know that z, we got its modulus as 2 units, so our r is 2, and then its argument is equal to 30. So this is how the complex number z will look on the Argand diagram. So secondly, we found z squared. Then we found that the argument of z squared was 60 degrees, and then its r value or its modulus was equal to 4 units. So that's how it will look. And then lastly, for 1 over z, we found its r value, its modulus as 0.5, which is the half we have here, and then it had an angle of negative 30. So negative 30 is represented this way. So the most important thing here that allows us to plot this correctly is we look at the angles that we are given. So that is what's going to direct us. So a positive 30 degrees is from here in this direction. So that helps us here. And a positive 60 is in the anti-clockwise direction. And then a negative 30 is in the clockwise direction. So that's what guided us in plotting this. Alright, so that's it for that number. So let's look at an example from UNEB 1989, and this was question 8a. So given that z1 is equal to 3 minus I, z2 is equal to 3 plus I, find the modulus and argument of z1 squared times z2 squared. And then number 2 was z2 over z1. Alright, so how do we solve this? Let's first deal with part 1. We have z1 squared times z2 squared. So now we know that we can find the modulus there. Alright, so before finding the modulus, we can see that this can be expressed in this way. Remember that from product of modulus, when you have the modulus of two different numbers adding, we can express it that way. So we have the modulus of this times the modulus of that, and then we can take the squares outside, so it will look like that. And then we can see that the answer we get from here will have a root of 10, because 3 squared is 9 plus 1, which is equal to root of 10, and then 3 squared here is 9 also, and here 1 squared is 1, so we have 9 plus 1, which is 10, so end up having root of 10 squared. Now you can see the squareds will make the roots cancel, then we'll remain with 10 times 10, which 10 times 10 is equal to 100. Alright, so moving on to find the argument, we know that the argument of something with a power is equal to that. Now we can see that when we're dealing with this, when we're dealing with an argument that has products, we can see that this first of all can be expressed this way, that this is the same as argument, that argument of z1 times z, actually argument of z1 squared times z2 squared can be expressed as argument of z1 squared plus argument of z2 squared. So remember this from the rules that we had actually stated. Then furthermore, because there are powers here, we can actually apply the rule of powers. You can see that these powers can go out, so we end up having 2 times z1 here, and then we have here 2 times argument of z2, and then we remember that actually now we can factorize out the 2, so the 2 can be factorized out, so we end up having that. So inside there we know that the argument of z1, so when we look at z1, z1 here we're dealing with a negative in the imaginary and then a positive in the real. So basically this is the fourth quadrant. So in the fourth quadrant we deal with a clockwise revolution. So that means we're going to have a negative on the tan, so it's negative tan inverse of, then we have a negative 1 over 3. But now because of this we're going to ignore the negative sign here when we find the answer, because that negative just simply represents a position on the imaginary axis. But this negative is important because of the clockwise rotations. Now on this other side, the argument of z2, we're dealing with a positive, so this is the first quadrant number. So that means everything is just kept as it is. So that's tan inverse of 1 over 3. So now when we press that in our calculator, we get a negative 18.4 from here. Then this gives us a positive 18.4. So when you add this, you get a 0. Then 2 times 0 is 0 degrees. So the argument is equal to 0 degrees. Yes, so that's it for part 1. So let's deal with part 2. So part 2, let's find the modulus. We know this can be expressed as that, and then we can actually see that the modulus of z2 is that, modulus of z1 is that. So we get root of 10 in both the numerator and the denominator. As you can see that this is basically equal to 1 because it's 1 over 1, and that will be the modulus. So finding the argument, we can see that the argument of two different complex numbers dividing themselves is the same as argument of them subtracting themselves. So the argument of z2 over z1 is the same as argument of z2 minus argument of z1. So remember this from the rules we'd actually stated, from the properties of arguments. So we know that z2 is obviously in the first quadrant, so that's tan inverse of 1 over 3 to find its argument. And then we know that z1 is in the fourth quadrant, so that means there is a negative in the argument because it's actually a clockwise revolution. So that's why we have this negative here. But because we are doing a subtraction, because there is subtraction sign, this is going to become a positive, of which we know that the answer from here is 18.4, and from here it's also 18.4, so we end up having them adding themselves. So the argument of z2 over z1 is equal to 36.8 degrees. Alright, let's look at another example from UNEB 1995. This was question 4a. So in part 1 we are being asked to express each of the following complex numbers. z1 is equal to 1 minus I, brackets 1 plus 2i, and then z2 is equal to 2 plus 6i over 3 minus I, and z3 is equal to negative 4i over 1 minus I in the form a plus b I, where a and b are real numbers. Then in part 2 we are being asked to find the modulus and argument of the product of z1, z2, z3 given in 1 above. So let's start with part A. So we're going to simplify each individual one. So we're going to first simplify z1. So z1 is basically the product of two complex numbers. So here we apply the rule of products. As you can see, when you open brackets, this is what you end up with. And as you can see, 2i minus I is equal to I, and you can see that I squared is equal to negative 1. So that negative 1 will affect that negative 2 to become a positive. So we end up having 1 plus 2, which is 3. So 2i minus I is I, so end up with 3 plus I. So now when we try to simplify Z2, let's go to Z2. Z2 is division of two complex numbers, and as you can know, we apply the rule of multiplying both top and bottom by the conjugate of the bottom. So this is what we end up with, and as you can see, when we open the brackets, we end up having that, and then this in simplified format will end up with 20i over 10. 20 divided by 10 is 2, so end up with Z2 being equal to 2i. So lastly, simplifying Z3, we can actually see that Z3 is also the division of two complex numbers. So we multiply both top and bottom by the conjugate of the bottom, which is equal to 1 plus I. So when you open the brackets, we end up having that. So right below, we know that I minus I is 0, and then we know that negative I squared is equal to a positive 1. And 1 plus 1 is 2, so we end up having that. So now splitting the 2 in between the two different numerator values, we end up having 2 minus 2i. So that's the simplified version of both of all Z1, Z2, and Z3. So we've expressed all of them in the form a plus b I. So now in part 2, we're going to find the modulus and argument of the product of Z1, Z2, and Z3. So finding modulus, we know that the modulus of Z1, Z2, Z3 is the same as multiplying all their individual moduli. So that's what it's the same as. So the individual moduli can be found like that. Then we can see that we have root of 10 times root of 4 plus times root of 8. Then we know that that is the same as root of 20. So all of them come to root of 20. And then we know that root of 20 is the same as 64 times 5, which is equal to, we know that root of 64 is 8, so the 8 goes outside the root, and then we're left with 8 root 5. So finding the argument, we can see that the argument of Z1, Z2, Z3 is the same as the argument of Z1 plus argument of Z2 plus argument of Z3 from the properties of arguments that we'd actually shown you before. And as you can see, that to find the argument of Z1, you can see that Z1 can be found that way, and then Z2 can be found that way. And that is because Z1 is going to be in the first quadrant, and then also Z2 is going to also be in the argument of Z2 is also from the first quadrant, so those are direct. And then when we go to Z3, we can actually see that Z3 has a negative on the imaginary, and a negative on the imaginary, that means it's actually in the fourth quadrant. So in the fourth quadrant, we have a negative, a clockwise revolution. So that's why this is going to be negative. And as you can see that here, the reason for the bars is the answer we get from here. We're going to convert that answer into a positive. So a 2 divided by negative 2 is actually equal to negative 1. But because of these bars, we're going to consider it a positive 1. So now this is going to be equal to that. So we get, and this gives us an 18.4. Then we know that by drawing this on our Argand diagram, when we place this on our Argand diagram, this is actually a purely imaginary number. So in the purely imaginary number, when you place that in an Argand diagram, we end up coming with 90 degrees as the argument. So this is going to come out from the Argand diagram as 90 degrees. And then when we come to this, we can actually see that this is going to be equal to negative 45, because tan inverse of 1 is equal to 45, but because of this negative representing the clockwise rotation, it's going to be negative 45. So we end up having argument of Z1, Z2, Z3 as being equal to 63.4 degrees, and hence we've solved that. Alright, so lastly I have some trial numbers for you that you should try out to get better at this part. So this is question number 1, and then I've given you some answers to actually compare with, so that you will know that you're on the right track. And then it's going to be question number 2, the answer is that. Then question number 3, you're going to solve those and try them out. Then question number 4 is going to be equal to that. So I encourage you to try this out in your free time to get better at this part of complex numbers. I hope this video really helped you. Thank you so much for watching. Thank you so much for watching this video. Thank you for watching to the very end. I am very, very grateful. I hope this video has blessed you and that it has improved your knowledge of complex numbers. If you really enjoyed this video or if it really helped you, feel free to leave a like on the video. And then if you're new to this channel, I encourage you to join our community by clicking on the subscribe button and then joining it, and then make sure to hit the notification bell so that every single time I upload a new video, you'll get updates on your notifications. See you in my next video.